Hello, my name is Scott Noble, and I'll be talking about 3D GRMHD simulations of accreting supermassive binary black holes. This work was largely done by Luciano Compi, Federico Lopez Orengal, Mark Avara, and Eduardo Gutierrez. And many of these individuals are moving on to new institutes, but Federico Lopez Orengal is on the job market, and I encourage you to seek him out if you're interested in performing similar work or new things with 3D GRMHD. And I'll be giving you an update of what we've been doing since the last symposium. We've been very busy, so without further ado, supermassive binary black holes are key multi-messenger sources for LISA, even though we may not see them with light and gravitational waves at the same time when LISA flies. We may see these systems with light beforehand, and we may learn about what to expect to see with LISA. So Ruben's going to see hundreds of thousands of these AGN, and even if a small fraction are binaries, we're going to see lots of them. So we're optimistic that we'll be seeing these binaries. There are some candidates, that we already know of, and so, but in order to really understand what we're seeing in light, we need to perform these sophisticated simulations to make accurate parameter estimations from the observational data. How do we go about doing that? Well, we need to perform, lots of different simulations. Here we've looked at the circumbinary disk, and we've measured how it changed as a function of mass ratio. So mass ratio from 0.1 to 1, 1 being equal mass. And we focus kind of on what happens to the lump. The lump is an overdense region in the circumbinary disk. So it's an enhancement in the density, and it's this orbiting structure that orbits at the local Keplerian rate and modulates the accretion and the luminosity of the system. And so we find actually that the lump kind of disappears for mass ratios greater than 0.2. Now, we also have found that the lump is sensitive to how much magnetic field there is. So the magnetic field, gives rise to this internal magnetic stress that then can maybe disrupt the lump. So if there's too much magnetic field, so on the column on the right, this is a space-time diagram of the magnetic stress per mass, we see actually that the magnetic field can disrupt the lump at a certain time, and but eventually it'll form again. So as the burst of magnetic field kind of disrupts the lump, that magnetic field will be accreted, and then the disk will settle into a natural state that the lump can then form again. So we found this kind of competition between the internal dissipation of the magnetic field from loops of opposite oriented field that are flung out by the binary into the lump region, and the rate at which magnetic field is accreted from larger radii. And we found that we predicted this threshold, and we found that all of our simulations, once they reach this threshold, that they form a lump. So, and then we also developed this new superposed Kerr-Schild system, where instead of matched spacetimes, so on the left, before we were using these matched spacetimes where there are different zones of approximation being used, and it was a little bit hard to include spins in the system because we needed to do these retarded time integrals that were very costly. So we developed the superposed Kerr-Schild system that is two Kerr-Schild solutions added together. And we find that it actually produces a vacuum spacetime pretty accurately, especially compared to the matched spacetime. So this is a faster means of calculating an approximate binary spacetime, and we use this to see how spins affect the accretion rate and the modulation of the accretion rate. And basically, in the circumbinary disk, the spin is not a huge factor. It doesn't change the gravitational field out there, but there is in the gap region there does seem to be a measurable effect, because the negative spin, so the retrograde spin oriented to the spin angular momentum, that kind of deepens the potential. Okay, and so that deepening of the potential can actually lead you to greater luminosity and accretion rate as it draws more material in. And whereas the parallel spins actually kind of help repel gas there. So because of the frame dragging effect. So there are measurable changes within the gap though. And so we wanted to also see how this affects the mini disks. The mini disks are expected to be the brightest feature of the system. And so we thought, well, spins are going to affect maybe possibly affect the jets. And in fact, we actually see that they also affect the mini disk structures because the spin diminishes the ISCO radius. What it does is it increases the volume of stable orbits in the mini disk region. Because as you see in the upper left-hand corner, with spins, the ISCO radius is much smaller. So the volume of stable orbits, so this outer radius is the truncation radius, these longer-lived mini disks then don't modulate as much because they're more persistent. Whereas without spin, they quickly form, then are accreted, quickly form and accreted, and so this is large amplitude modulation. We've verified also that the mini disks around spinning black holes have specific angular momentum that are nearly Keplerian, whereas the non-spinning ones are sub-Keplerian, and so they form these spiral arms that just kind of plunge into the black holes. So we do see powerful outflows from these spinning black holes, as you would expect. So there's a significant pointing flux now coming from these black holes, and these jets are modulated also from the accretion rate from the lump or the circumbinary disk and through the mini disk accretion. And we do see that the pointing flux luminosity is modulated at 2 times the beat frequency. So there is lump, dependent phenomenon in the jet emission. We find that there's significant enhancement in the radiative efficiency in the pointing flux and the hydrodynamic flux with spin. So it goes from a couple percent to 5% in the electromagnetic flux and 2.5 to 10% in the hydrodynamic flux. We also did a post-process radiative transfer calculation to predict the spectrum. On the right, we compare a single black hole model. So you take the total mass of the black holes and you create a Novikov-Thorne model. Actually, it's not Novikov-Thorne. It's connected to a simulation of a radiatively efficient accretion disk simulation that we performed around a single black hole. And we created a spectrum from that simulation, compared it to one of our binary, and we see that there's a softening in the thermal spectrum because portion of the disk is truncated now because of the gap, and so we lose radiation there. It's not fully moved to higher energies with that you would see, so that you would think that some of the mass would then lead to radiation that in the mini disks, and that would take some of the power. We do see that there's an enhancement in the mini disk temperature region here, but it's not higher than what you would naively expect from Novikov-Thorne models shown on the left, because there's enhanced accretion due to internal shocks in the accretion stream that allow for the gas to plunge more faster into the black holes. So this was kind of a surprising result, and this leads to a pretty different spectrum than for a single black hole. There's significant variability differences too. I won't go too into this, but we see actually that the both spinning and non-spinning black holes show variability on the lump timescales. The non-spinning one has more variability at the beat frequency between the lump and the binary orbit. So at a higher frequency than the binary orbital frequency. But with spins, there's less because that there's less variability in the mini disk accretion because they're more persistent. We've also been looking at longer term evolutions of binaries and to kind of connect to Newtonian simulations and results. So on the top left shows the angular momentum gradients and shows that there's good equilibrium. So the red line shows the net angular momentum flux, shows that it's flat and predicts a value of 0.68. Our simulations tend to predict a value around 0.5. So that means if it's below this pink dash line, it means that the binary actually inspirals. So accretion enhances in spiraling. But if it's above it, it wants to wants to increase the separation of the black holes. So it seems like our GRMHD simulations predict something closer to the threshold value. So this issue may not be completely solved yet. So I just want to say thank you for attending my talk. There's some open questions still that we're trying to address and trying to figure out. And if you know the answer to any of these, I'd love to hear from you. And thank you again.